So today's lesson's on 8.B.1, which is Introduction to Coordinate Proofs. Now we've actually been working kind of on coordinate proofs before today when we were working on 8A, but that was not where we used numbers on everything. We did not try anywhere it was more applicable for every single type of parallelogram or every single type of triangle. And so today when we get through, we're going to still use our formulas that we learned in the last unit, which that's why we started with that. But the goal with today is to try to figure out, well, how is this going to be true for all of that same polygon? So it says coordinate proof is a proof that involves placing geometric figures in a coordinate plane. And it says, note, when you use variables to represent the coordinates of a figure in a coordinate proof, the results have to be true for all figures of that type. So that means like all triangles or all trapezoids or all parallelograms. That's the goal that we have to be able to come up with. So here are the formulas once again, just to kind of have them all in one place from last week. The distance formula is what we're going to start with, which is d equals the square root of, remember you subtract the x's, but the order here is not very important, because when you go to square it, it's going to remain a positive. So y2 minus y1 squared, remember that's what was the distance formula. So nothing changed so far with that. The midpoint formula was the next one that we did. Midpoint formula was where you add up your x's, so x1 plus x2, and you divide it by 2. Same thing for your y's, y1 plus y2 divided by 2. That's how we found our midpoint. And then finally, slope was thrown in there. We used that quite a bit, and we will continue to. It's y2 minus y1 divided by x2 minus x1. And we did need to remember the order matters for slope here. Y's are on top, x's are on bottom, and the order that you subtract your y's, it's going to be in that same order for the denominator. All right, so now let's go ahead and try out a coordinate proof, and what we're going to need to do on all of these is make a sketch. But we don't really need graph paper for this because, remember, we don't have points, we don't have numbers anymore. We're going to have variables because it's more, it's going to be true for all figures. So it says sketch triangle ABC, where A is the origin, 0, 0. B is sitting at this point P comma Q, which I don't know what P and Q are yet. And the last point I'll give you here, C, is going to be at 2p comma 0. And it tells in this parentheses that p and q are greater than 0. All that's telling us is that it's like a criteria that we're always going to have to make sure they're positive numbers, because that would get really complicated if p was anything or q was anything where it could be a positive or a negative. So this makes it easier. You don't have to write that down yourself. So I will always give you the problem, like with the coordinates. Our goal is to graph it. Now p and q are also not equal to each other, so we know that they're just different numbers, but they could be any positive number. It could even be a decimal technically, but we're going to try to, we're not going to really identify what they are. So what you do is you start by making yourself a coordinate plane. We only stick in our first quadrant here because it says p and q are greater than 0, so we're staying positive. The easiest point to plot first is your A, obviously, which is at the origin. So you want to label it A. You can also put the coordinate there, 0, 0. Then we're going to label our other 2 points. Now, P, Q means the B value has to go P units to the right and Q units up. But we don't know what they are, and that's okay. You can pick kind of the location. So let's say this is B. If this is point B, I have to think about kind of, and I'll label it P, Q. That means then that I went P units horizontally, right? And then I went Q units up. So if it helps you to kind of label on this, you can say that's Q, like it could just be some number, and this would be P. So if C is sitting at 2P comma 0, then that means that it's the same distance away. If this is P, I have to go P a couple, like further out, and then if it's at 0, we know it's on the x-axis, right? This is my x-axis, this is my y-axis. So this is point C, it's sitting at 2P comma 0. So I've labeled my sketch, right? I can draw out my triangle here. And the question says to classify the triangle by its side lengths and the angle measure. So looking at it, you can kind of look at it and say, well, maybe it looks like the legs might be congruent, but maybe it looks equilateral. I don't know until I actually find my distances using distance formula. So this is what a coordinate proof does. You're still using the distance formulas like we did in the last unit and the last quiz from yesterday. The only difference now is you're not using numbers, you're using variables. So let's go ahead and find the three distances, AB, BC, and AC, using the distance formula. The only time you don't have to use the distance formula is when it's a horizontal line like this, where we could just count the units technically, or how far away, using just looking at the x-coordinates. Or it's a vertical line, same idea. But you can always use a distance formula. So let's go ahead and use it here. Subtract your x's, p minus 0 squared, and subtract your y's, q minus 0 squared. It equals, when you're simplifying this, p squared plus q minus 0 is just q, so q squared. Now here's an important piece here. A lot of times people look at that and say, well, should I go further? Should I write that as p plus q? You actually can't. When there's a plus sign there, when it's a square root of even perfect squares like p squared and q squared, you cannot simplify further when you see plus or minuses, right? So if this was just the square root of p squared or just the square root of q squared, then we would have to simplify further, but since it's not, we stop right here. And that's my answer for the distance for AB, the length of AB. Do the same thing for BC. So we want to subtract your x's, 2p minus p, and square it. And then my y's are, I'll do q minus 0 squared, though you could write 0 minus q. It's the same thing. But notice I get the exact same answer because 2p minus p is just 1p, and then I'm squaring it. Q minus 0 squared is again q squared. So far, this is looking like an isosceles triangle because I have two legs congruent. These two are congruent so far. I just need to see, is it going to be equilateral or isosceles based on the third side. So here's my third side here, A to C. If you want to use distance formula, you can, but if you notice here that this is p units to the middle and another p unit, so like all of this is 2p units, that's actually your side length, right? Because p is just some kind of measurement. But if you do want to use the distance formula, here's what it would look like. 2p minus 0 squared and then 0 minus 0 squared. So this would be 2p in parentheses squared. When you see a square root and a squared, you can technically just cancel it out, or you could simplify this further and write 4p squared, because that's what 2 squared and p squared is. And then you write it as 2p. So two sides the same, one is different. So this is an isosceles triangle. Now you can tell by looking at the slopes. I'm going to look at the slopes here if this is going to have any right angles. Otherwise, it's going to just be acute isosceles. Okay, so we don't have to worry about figuring out if it's what the angle measures actually are. It's not asking for that, but we could do that if we created right triangle, if we drew a straight line down. Let's make sure angle B here is not a right triangle, because it could be technically. To do that, we have to look at slopes. So the slope from A to B, this is the slope formula, q minus 0 over p minus 0. So this would be q over p. Right? Think of rise over run. The slope of this one, you're going q minus 0, if you need to write that down, we can, over p minus 2p. So that comes out to q over negative p. These are not opposite reciprocals. They are reciprocal, or they're opposites, because one is a positive, one's a negative, but they both have q and p in the same location. And then horizontal lines are always 0 slope. Right, so m is 0 on that one. So that's the, noticing the slopes here, then this would mean it's an isosceles acute triangle. Okay, so then we're going to keep going. It says to find the coordinates of each side's midpoint. So to find the midpoints, let's label them. Midpoints are going to go exactly in the middle of each of these. So I'll label them with D, E, and F, just so we can label, talk about them with letters. And if it helps to do it in a different color, D, E, and F. So here is D. To do the midpoint of letter D, or to find midpoint D, you want to add up the x's, so of A and B, p plus 0 over 2, and add up your y's, q plus 0 over 2. And when you write that as a simplified fraction, or just reducing it, just p over 2 and q over 2, because 0 doesn't really do anything. All right, you do the same thing for E. My point E here, I want to do P plus 2P divided by 2 and Q plus 0 divided by 2. So again, just using the midpoint formula. The first one comes out to 3P over 2, which you could write as 1.5P instead, and then just Q over 2. Notice that the two midpoints we just found are exactly on the same y values, and that makes sense that it would be kind of like a mid-segment there, you can imagine. All right, and finally F, you don't have to actually look at like using the formula. You could just say what's halfway between 0 and 2P, and it would have to be at P. So we know it's P0, but if you do want to show work, here is the work. 0 plus 2P, 0 plus 0. So that comes out to just 2P over 2, and then comma 0, which is really P comma 0. Which you don't need all this work for if you just look at the diagram and say what's halfway between 0 and 2P. Alright, we're going to try a couple more of these out. Same concept, but just again trying to figure out where they fit in the, how to write, like using the distance formula and so on to find what's needed. But now the next two, we won't have coordinates given to us. Let's see what to do when we have to ourselves create a figure. So the first one we're going to do is a square. When it says place each figure in a coordinate plane in a way that's convenient for finding side lengths, always try to make it so that you're using your like origin for one of the vertices, and try to use the axes to help too. So like for a square, we know we have 4 right angles, and so we have lots of horizontal and vertical lines, two sets of them. So like for example, I can use this set of vertical line with this set of horizontal line, and then we know that the top has to be exactly parallel to the bottom base, and it's the same distance. So when I create this, there's a vertex there, vertex here, and here. You're just making a square with the 4 right angles. Let's think about coordinates now, because we have to label our coordinates. Obviously you have 0, 0 for one of them. Now the same distance that we go up here has to be the same as what we go to the right, and so you can pick a letter to represent what that distance is. So I'll just use C, right? So C units up, C units across. That would mean this point is written as 0 comma C, right? Because it's sitting on the y-axis. This point then would be C comma 0, because you're going C units to the right. And then finally, to come up with this corner one, you have to look at what are my x and my y coordinates. You went to the right C, and you went up C. So C comma C. That's how we would do the square. Next, let's try an equilateral triangle. Okay, so think about what we know about equilaterals. All 3 sides are the same. And also here, angle measures will come in. You know that equilateral triangle has 60-degree angle measures. So first let's start off with just the first quadrant. We're always going to stick in the first quadrant because it's easier. Pick one of the vertices of your equilateral triangle to be at the origin, because again it's easier. And I'm not labeling it with letters, though you could. So I'm just going to first draw it out, like try to make it as perfect as I can, and then we'll label our points. So we know equilateral triangle will have 3 sides that are all the same. And let's think of the angle measures. We know it's 60 degrees there, 60 and 60, but here's what we're going to have to do. Kind of use our special right triangle rules here, because if I draw down this straight line and kind of split it into a 30, 60, 90 triangle, we know that based on whatever the short leg is, which I'm going to use C again just to represent the short leg. You could use any letter you want. If this is C units, then I know that this height here would have to be C root 3. Because remember, short leg times root 3 is your long leg. And the hypotenuse is always double the short leg, so 2C. So I'm kind of labeling my triangles. Remember, this left-hand side triangle is the same as the right-hand side. They're identical. They're still 30, 60, 90, so this is also C. So now let's see if we can come up with our coordinates. We already have the 0, 0. Let's try this bottom one first because it's easier. We know that the y-coordinate has to be 0 because it's sitting on the x-axis, and the horizontal distance here is C plus C, which is 2C. And that makes sense because all 3 legs are going to have a measurement of 2C, as you can see by the hypotenuses of those. So 2C is like the measurement of the legs. Now finally, to label this point here. the y value for this point is the height of this triangle, which we just came up with, which was c root 3. So that's my y value. And then the x value, notice it went c units to the right, so c would be the x value. And so those are my 3 coordinates. Okay, we're going to do a couple more examples onto the back here. Alright, so finding the length and the midpoint of any diagonal of any rectangle is what we're going to start with. So we're going to draw out our sketch. Here's my coordinate grid, and then we'll do some work to show that the diagonals are what the diagonals are for the lengths and the length and the midpoint of those diagonals. So first, let's come up with our coordinates. Obviously, 0, 0 again for my rectangle. Draw out a rectangle. It could be any way you'd like. You could draw it like this, or you can make it longer on this way. It doesn't matter. But we do know that the legs are not all, or the sides are not all the same like a square. So let's pick some variables again. So I'm going to say it's A units here and here. Let's say it's B units for the other two sides, so that A and B are different. So to write this point here, I want to call it 0, comma A, because again, I'm on the y-axis. So 0 has to be the x value, whereas the y here has to be 0 because I'm on the x-axis. And you went B units to the right. So B units, and then didn't move anywhere up or down. So then this point is in terms of the two other points that you just did, where you went right B and you went up A. So B comma A. And it helps if you actually label our rectangle, let's call it MNOP. Because now when I'll find midpoints and I'll find diagonals, it'll be easier to do. So let's start with the diagonals. One of the diagonals is MO. The other diagonal is NP. So using my coordinates, I can show that the diagonals of a rectangle are congruent. Let's show that that's true. So here's my distance formula again. B minus 0 squared are my two x's, and I am adding x, or A minus 0 squared for my x's, or y's. So this would be square root of B squared plus A squared. Now technically the order there does not matter, but that's what I get for my one rectangle. Do the same thing for the second one. So we have A minus 0, or sorry, B minus 0 this time. Again, because the x is subtracted, and then the y is subtracted, either 0 minus A, or you can say A minus 0. Remember, the order does not matter here. B squared plus A squared again, and we see that they're congruent, which is true for all rectangles. Then we're going to try to find the midpoint here. So the midpoint of any one of those, you can use the either diagonal to find the midpoint. The midpoint of, like, let's use this one, MO, would be add up your x's, 0 plus b divided by 2, add up your y's, a plus 0 divided by 2, and then just simplify. So the midpoint, which you could label with a point if you want to, would be b over 2, comma a over 2. Right, so that was for a rectangle. We found the distances using the distance formula. We found the midpoint using the midpoint formula. And you just want to make sure that you draw your diagram first and you can pick your letters. That's what kind of makes this a little bit challenging, because there are so many ways that you could pick them. But just think about, what do I know about rectangles? I know the opposite sides are congruent, but they're not all four the same. So we're going to try one more, which is use coordinate geometry methods to prove that the diagonals of an isosceles trapezoid are congruent. So we learned this back in Unit 5, that the isosceles trapezoids have diagonals that are congruent. So we're going to go ahead and draw it again, draw it first, and then use the distance formula to show that the diagonals are actually congruent, because you should get the same distances for both. So let's draw my sketch first. Because again, once you have this done, then you can actually get to the actual algebra. So again, always try to use an ordered pair at the origin, and you can label it. I'll do my isosceles trapezoid this time. We'll do LMNO. So this is my first point. Now when you think about a trapezoid, I'm going to put my base, the longer base, on the bottom here. So I'm not going to label it yet with letter, I'll actually just call this O. So it's L, and then M and N are going to be up here. Now if it's an isosceles trapezoid, think about what you know already. You know that the legs are congruent, so I'm going to try to draw it so that these legs are congruent, and then I'll label so far just the letters, M and N. So we know M and N are the same height. The Y values for them should be the same. You have to figure out, though, the X values kind of for everything. So let's start with this one first. This is just telling me to go a certain distance away, all the way, and then stay at 0. So let's say I want to do A, comma, 0. So this whole distance here should be A, all the way, the base. The larger base is A. Now, in terms of coming up with this point here, you're going to actually have to use the previous, this A that we came up with, because the whole distance here is A, but I want to figure out what is this distance. It's not related to the A. Okay, so this distance there, you can call a different letter, which I'll use B. Okay, so again, we're talking about from here to here. That's B. That's what I'm choosing to be B. So thinking about your distances again, my M could be B, comma, and then the Y value I'm going to say is C. It's sitting up at like C units. That means N also will have a C for the Y value, but now we have to be careful with how we write our point here for the X value, because N is related to both A and B. Because if I think about it, this whole distance is A, but I'm just taking away this portion of it, which remember is B, because these two triangles are, it would be isosceles triangles here, or it would be the same triangles because these legs are the same. So whatever that distance is also the same here. So I want to tell it to go all the way to A and subtract B. So A minus B is what that would look like. I know that can seem a little confusing. We will practice more of that. So now let's go ahead and find the diagonals. So LN is one diagonal and MO is another, using the distance formula. So we have subtract your x's, A minus B minus 0 squared. Now that looks a little odd, but 0 doesn't really do anything. Same with the C minus 0 squared. That comes out to, when we write this, you can't do anything to the A minus B because it's just A minus B still inside, and you're squaring it, and then that's still C squared. You can't write this as A squared plus B squared. You can't distribute it or anything. That is as far as it goes. Let's do the same thing for MO. Let's see what we get. MO would be A minus B squared, or A minus B in parentheses and then squared, and then C minus 0 again, squared. So yes, we get the same answer again for the diagonals. So they are the same. The diagonals are congruent, like we know already, for an isosceles trapezoid. All right, and then we will finish up with one last one, and we will go over this some more on Wednesday as well, because I know this is a tough concept. We're going to kind of keep working on it all week. The last one we're going to try to prove is that the medians that are drawn to the legs of an isosceles triangle are congruent. So again, start off with our coordinate. We need to make an isosceles triangle. So like we did kind of on the, we did work with on the front example, was sort of isosceles, but that just means give yourself the legs that are congruent, and then the last leg won't be. The base will be different. So let's try to label some stuff. Again, 0, 0 for the origin, which I'll call this time point O, and then I'll call this P and Q, just to change up some letters. So let's do kind of coming up with a distance here. I want to pick a number because when I do medians, I'm going to have to look at midpoint. That means when I pick variables here, I want them to be even numbers or have a multiple of 2, because when I cut it in half to find a midpoint, that I don't want to deal with too many fractions. So for this Q here, I'm actually going to pick the point 4a, comma 0. And you'll see kind of why I did that once we get started. I know it's hard to come up with on your own, but once you try these out, it should make more sense. That means then that this distance between this to this, if the whole thing is 4a units, I want to go halfway, so I want to get to 2a for the x value here. And then you can pick whatever the y value should be here. I just picked b. But again, instead of it being b, I want to double it, and you'll see why in just a second once I start doing my midpoint formula. Because midpoint formula, you're going to get this midpoint and this one. And when I find those midpoints, I don't want to deal with so many fractions. If this was just a and b, then that would have meant I'm going to have kind of cutting it in half. So the reason, again, this is halfway right? It's an isosceles trapezoid, so triangle, so this distance is the same as this one, all the way here. And so, because again, these triangles would be the same. So if this is 2A, I have to just add another 2A. That's where that 4A comes from. And now let's find our midpoints. So the midpoint of OP, which actually, instead of writing that, let's go ahead and label these M and N. So it says, again, you're trying to figure out what the midpoints are because you're trying to show that the medians are congruent in an isosceles triangle. Here's a median. This segment is a median, and this one is too. And so we're going to show that these two segments, MQ and NO, are congruent. MQ and O. And so first we need to find the midpoints. I'm going to write them down right next to it. Okay, so the midpoint for M would be halfway between 0 and 2A, so that's A for the X value. Halfway between 0 and 2B would be B. So A comma B is my midpoint for M. Same idea for N, but you want to do halfway between 2A and 4A, which would be 3A, and halfway between 2B and 0 would be B. If you're having trouble with those, though, you can just use the midpoint formula. So now that I have those, though, let's use the midpoint, or the distance formula, M to Q, 4A minus A squared, plus B minus 0 squared, and then simplify. 4A minus A is 3A, but make sure you put in parentheses and square it. This is plus B squared. This 3A should be squared, so that comes out to 9A squared, and then still plus B squared. And that's as far as you can go. Let's make sure we get that same answer for NO. So this would be square root 3A minus 0 squared and B minus 0 squared. That comes out to 3A squared would be, again, 9A squared. You have to make sure to square the 3 and the A, and then plus B squared. So yep, they are the same, and we are done. So again, homework today is 8B1. Make sure you're trying it out. Even if you're struggling with this a little bit, check the answer key on the website to make sure you're doing these right, but definitely give it your best shot. And we'll go over more of this on Wednesday. Or I'm sorry, yeah, on Wednesday.